Welcome back, everybody. So we're going to start out with this Bayesian example, but I want to make a couple announcements. I updated the webpage, just kind of reminded you things that we've done so far. We're about out of probability land and into inference. We have spoken about inference in terms of utilities of the Bootstrap and Delta method and some Bayes. So we're about to get started with comparing all those things. I do believe that statistics is a comparative field. And there's nothing better to me than exhaustively comparing two techniques. And I'm going to ask you to do that in an upcoming homework assignment. So just bear in mind there's a new homework out. I call it homework 3, although it could be homework 4, depending on how you count. And I have this due after spring break, so that I'm not going to burden you with typing up your answers and doing all of that stuff. But there's a couple little problems in here concerning chapter 6 that deals with different principles of inference, and some of them are a touch more practical than others. I've gone back and forth whether or not I like teaching the likelihood principle. It's one of my love-hate things. And so I can't help myself but to talk about the likelihood principle a little bit. So we'll discuss it, and then we'll discuss whether or not techniques violate the likelihood principle and whether or not it matters. So we'll include it in this course just in terms of whether or not you violated a certain principle and whether or not it matters. So I used to agonize over this. So did I just violate the likelihood principle? Something like that. Am I going to statistical prison? So saying that, if there was a statistical prison for violating the likelihood principle, we'd all be there already. So we will discuss what it means, and I think about some of these principles as guiding light. We'll jump into the sufficiency principle, hopefully by the end of this lecture. We'll see how far we get. But I want you to work these problems. They'll help you out with the exams. Hopefully I can ask a question from chapter 6. So I will cut the exam off in terms of the material that we cover after next lecture. So we'll probably be able to say something about sufficiency. Just in terms of a point of reference, we're giving the midterm 1 2 weeks earlier than I gave it last year. So I can't quite cover as much. So good strategy on your guys' part. So let's get it done early, and then we don't have to have so many results that we need to be responsible for. I have published the code for the Bayesian beta, I call it the Beta-Binomial example. You might call it the binomial beta example. And so that's online, so you can look through this code that we started looking at last time, and we'll finish up this time. And then I also give you a new homework assignment, and it's called Delta, Boop, in Bayes, and that's the comparative study. We'll look over this on Friday a little bit, but basically it says for this example where everything is binomially distributed or Bernoulli, right here we're going to try to estimate this parameter p over 1 minus p. I'll say a little bit more about that in terms of Bayes, but in terms of Bootstrap, you should know how to do that and estimate it. So basically you do a Bootstrap replication, you compute x bar, and then you plug it into that equation. Solve for p there. You do it over and over and over again, and that's going to have different performances depending on what p is and depending on n. So you're going to devise a simulation study with various configurations of n and p, and they're right here. Before you do that, I do ask you to go through the delta method and show the theoretical result and see how it applies to different data sets. So, and you can get a hang on how you use the delta method inferentially. Again, I'll say more about this next time, but if you want to get a head start and look at this homework assignment, it's here. It takes a while to read through. It's 3 pages of writing. And I do mention some potential pitfalls and what you might do about it all. So read through that and we'll discuss it next time. So I do want to pick up with this example that we were on last time. So just a quick reminder, next homework is due the written problems. I think there's 5 or 6 of them. They're due on the Monday following spring break. So that should give you ample time to play around with it. But hopefully you're coding up this example over spring break. So there's a lot of things to do. There's coding it up, all the data storage, the analysis, thinking about it all, and then writing up the results of everything. So it does take some time. So have a look at that. So this is where we were last time. I'm just going to remind you the problem. So the example is xi's are coming from a Bernoulli with parameter p. Everything's an IID. And I'm going to flip the coin n times. In a Bayesian manner, I'm going to try to infer p. So how does Bayesian do that? They do two things. So to do this in a Bayesian, you need the likelihood function, that looks like this, p to the xi, 1 minus p, 1 minus xi, everything's IID, so I can just product across this. I'll just remind you this thing is proportional to, it's actually equal to that. So I'm going to write this down in terms of binomial formulation, where this x is now encoding the sum of the xi's. And I can write this problem out in terms of p to the x, 1 minus p to the n minus x. And really, I'm just reminding you these two functions are proportional to each other. So if you were thinking about the binomial model versus the Bernoulli model, those likelihood functions are proportional to each other. We'll come back and we'll keep discussing this. So I'm setting you up for the sufficiency principle and the likelihood principle by writing this out. Hopefully we'll have time to see that example. So, and we need a prior. In our prior for this example, might be the conjugate prior, and it would look something like this. P to the alpha minus 1, 1 minus p to the beta minus 1. And so this is a beta distribution. It looks a lot like this function right here. Keep in mind, in terms of the sampling model, x is the random thing, but once I see data, and I plug it into this equation, I think about this as a function over the parameters, that is now a likelihood function. An entirely different function, but it has the same mathematical relationship between the data and the parameters. I think it's a good idea that you use that relationship when you do inference. It makes sense. It might make so much sense to you that you're like, why do I need any convincing of that? So back in the 1920s, through, I would say, the 1980s, a lot of people needed a lot of convincing that the likelihood function is worth talking about. I'll bring in some commentary about that debate. So things that we take for granted and we're just supposed to swallow, people used to fight about. People sometimes still fight about the utility of likelihood functions. I'll try to convince you by the end of the class, whatever you do, use likelihoods. So it's a good idea. So if I multiply these two things together, I'll just write this out. We form our posterior distribution. And I'll write it out in terms of x1 to xn. So this is going to be proportional to the likelihood, x1 to xn, times our prior distribution. And this is going to be proportional to p to the sum of the xi's plus alpha minus 1, 1 minus p to the n minus sum of the xi's plus beta minus 1. And so this thing looks like a beta distribution. And how do I recognize the parameters of a beta distribution? I always have this minus 1 sitting there. I never try to absorb it because I can recognize the parameters of the beta distribution just by looking at what's to the left of the minus 1. Usually I just nickname this and I'll call it alpha tilde, beta tilde. And so in a conjugate analysis, all you're doing is updating the parameters of your distribution. So our posterior distribution is beta, the prior is beta, so that's a conjugate prior. And we want to understand what is this distribution right here. I don't think a lot of us have a lot of experience with betas. What I want to emphasize is how flexible they are. So let's just run to this example. Pick up where we were last time. You can play around with this code a little bit more at home. So there's a few parameters in here. If I'm going to simulate everything, I need a truth. And to be a fair statistician, I'm not going to use the truth in my inference. If you ever do use the truth in your inference, so if I'm trying to infer what P is, and I need knowledge of P and I plug it into the equation, you're not a statistician anymore. So you have missed the entire point of everything. So we're trying to learn P, so if you use P, true P, to learn P, you've made a mistake. You should just use P itself. I'm saying this because every single year I've taught this class, I ask people to infer something. So usually I call the parameter space beta and the data space X. And every single year, it does not matter, without fault, on either a midterm or a final, when I ask somebody to infer theta, they'll come up with an equation that includes theta. And it drives me crazy. So if you include theta in your equation to infer theta, you have made a critical error and you do not understand what statistics is all about. So again, if you knew theta, you just report it back and you wouldn't mess around with it. Every single year. That is my biggest pet peeve in this class, the inference class, that sometimes people will use the truth to infer the truth. You can't do that. So my next biggest gripe I'll tell you about later on, but it's things like dividing by matrices. So stuff of that nature. All easy stuff to fix up. Okay. We'll talk about some of the other critical errors and hopefully you don't make them. I'm curious to see who's going to do it. It's going to be one of you. I hope it doesn't happen. Okay, so we do need the truth to simulate the data. That's P. And then we've got our hyperparameters, alpha and beta, and they show up in the posterior equation like this. And then I have some number of iterations, that's N in our calculation. So just cap it. So let's pick some values. I think I picked 0.7 last time, so we'll stick with that. Slight issue, it doesn't show up numerically is a problem in my model, but if I was actually doing a real integration, it would be a problem. So alpha and beta are supposed to be greater or equal to 0, but you can't set them equal to 0. It's possible. So that's called Haldane's prior in this case, and there are some properties of that prior that people enjoy. So, but I'm going to say that we're going to use a proper prior, meaning that that is an actual distribution. What I mean by that is if you integrate over that distribution, it doesn't blow up to infinity. It's a normalizable distribution. So an improper prior gives us an example, a uniform across the real number line between negative infinity and infinity. It does not integrate. You could never sample points like that, but you can think about it conceptually. Our domain, our space lives between 0 and 1. And so we don't have that unbounded thing. So I'm going to pick some values. This is what we picked last time, something close to 0, and beta is a 1, right here. I'm going to flip the coin some number of times, so I'll call that 10. I just want to point out, our prior, pi p, is proportional to p to the alpha minus 1 minus p to the beta minus 1. So alpha is associated with p, the success, so a heads of the coin flip, and beta is associated with fails. Does anybody know what the expectation of this model is? Very good. Alpha over alpha plus beta. So this is just a ratio. And it's in terms of P, which is success, the coin flip. And so alpha compared to alpha plus beta is basically showing up in terms of a prior frequency. You could think about it this way, that if I conceptualize the prior in terms of a fictitious number of coin flips, and I'm weighting my analysis using that, then alpha is showing our fictitious number of successes and beta is showing our fictitious number of fails. So we could interpret it that way. We could interpret alpha and beta in terms of data points, in terms of weight. If we think about our posterior distribution, alpha shows up additively right next to the sum of the xi's, the number of successes. And so it's acting like a data point, the success. And beta is acting like something like the number of fails. And so when we came up with this prior right here, we weren't thinking about that per se. We're just showing what the impact of the prior is. And basically this prior, in terms of how we might interpret it, is we might be thinking that my prior says that I've seen one fail, that's beta, in approximately 0 successes. And so that might be the interpretation of this prior. So this prior in some sense is acting like 1.0001 data points. So we'll see what that looks like. So let's just flip that point. So this is what my prior distribution looks like, beta. So beta is constrained to live between 0 and 1. So that dashed line is the prior density function. This is my truth. It's not placing much weight on my truth, but there is some mass here. And so I will say, in terms of being a Bayesian, if there's any potential values that are possible, you need to put positive mass on those. If I had a prior that didn't put positive mass in this region, but 0 mass, the likelihood function, when I multiply across that, can never put mass in this region. So if a priori you think something is impossible, no data will change your mind. I tend to think of that as a political prior. So, or dogmatic priors is the way that I think about it. So don't try to change my mind with any data. I already have an idea of what's going on. So we see that in some places. Hopefully we don't do that in science. So that's the prior distribution. Let's flip the coin. So my first draw is a 0. And so what that means is that my likelihood function is 1 minus p, and that's that new dashed line, that red dashed line. So that's 1 minus p is that line. And then if I multiply the prior into that line, right here, so I'm just multiplying in a pointwise fashion, these values right here times those values right there. And once I normalize everything, that creates my posterior distribution. And so my posterior distribution looks a lot like the prior in this case, and that's what we notice. Doesn't look a lot like the likelihood. So the prior has a lot of weight, but keep in mind the likelihood only has 1 data point. And so basically the likelihood and the prior have about the same amount of weight. If I flip the coin again, I get another 0 right there, and my likelihood just bent. So it's not a straight line anymore. It's 1 minus p squared because I just saw 2 fails. If I multiply that into the prior, it looks like this. Flip the coin again, we just saw success in this distribution change quite dramatically. And it did something really important. So it ended up placing 0 mass on, or 0 density, I should say, on 0, and it also has 0 density on 1. So we know that it's not absolutely certain that we're going to see a fail or a success. And the likelihood function is responsible for doing that. Our prior didn't do that for us. And so now we've noticed that after these 3 coin flips, our posterior distribution looks totally unlike either one of these things, the likelihood or the prior. Rather, it's something in the middle. So And I usually say it's a superposition of these two things, meaning that I'm just multiplying values of the prior against values of the likelihood, and that's giving values of the posterior distribution. I have normalized everything, so everything under my curves adds to 1, and I normalized my likelihood function as well, just so you could see it on the screen. But I could have multiplied my likelihood function by any positive constant, but it wouldn't have scaled well and you couldn't see it, so I just did this for convenience. So if I flip the coin again, 4 coin flips, I see another fail, and so I'm placing a lot of mass over on to the left of 0.5, because I've just seen 3 fails and 1 success. Flip the coin again, I just saw a success. I saw another success, boom, boom, boom. We're starting to see something happen, where my posterior is starting to look more like my likelihood function. So as you get more and more data, your likelihood starts to peak, and it becomes more concentrated. The prior doesn't change. And so that peakiness of the likelihood function, we'll call this consistency, and we'll get around to these definitions later on, is what's really driving the analysis, I would say. So I just flipped the coin 10 times, and here's my answer. So my posterior distribution says, essentially, I think that P is somewhere between, I don't know, I'm just going to eyeball this, 0.1 and 0.85. And so that's the way I interpret this. If I were teaching Stat 101, I would show people a lot of likelihood functions. I think that this really is the driving force of inference. And so thinking about likelihoods is important. What you do with them is a question. So the Bayesian knows what to do with them. They multiply by prior and interpret it as a probability distribution. And so our truth is over here. The reason our truth is so far from the real massy part of this distribution is because n is small. And that's all there is to it. So let's do it again. Also, I should say that this prior is pulling everything to the left-hand side of the likelihood. So in terms of just the data, it's that dash curve. It's a little bit more to the right. Okay, let's do this again, but I'm going to speed it up a little bit. So I just put in a pause statement, so if you want to fiddle around with this code, just remove that pause statement. I have another pause statement in here that just pauses everything for 0.01 seconds. Do you know why I do this? I put in this quick look. You see the result, but it updates the figure. So it takes a pause and it'll render the figure. And if I didn't put that in there, the figure would get updated all at the end. And don't debug my code doing this sort of stuff. I do it for illustration's sake. So this is about the slowest thing you can do on a computer, stop and render everything. Even print statements to the screen slow down your code a lot. So I do it, and usually I just do it periodically. So I would do this like every 10,000 iterations. I might print something back to myself. So let's rerun this. See how this evolves. We can see what happens. That's how Bayesian thinks. That's what this equation means. So, and I'm updating it after each coin flip. And so, it looks pretty good. For a second there, it didn't look so good. It was like, you better start getting over to the right, you know, if you're going to flip it that many times. And it did that. And early on in the analysis, the prior had some weight. And I'd consider this is a prior that kind of represents to me that you think that I'm flipping a biased coin. So prior had a lot of impact early, and it had a lot of very little impact late. I want to point out also, early in everything, the posterior distribution, this beta distribution, didn't look normal at all. It looked something totally different than normal. And later on, as we ran this for a bunch of coin flips, that distribution starts to look more and more normal. So I'm going to point out the statistic that appears, the only thing that this function depends on in terms of the data is the sum of the xi's. That's something that has the central limit theorem attached to it. And so if we were doing a delta method sort of approximation or something like that, we'd get something normally distributed. You wouldn't have to do delta method just for inferring p, because you would just invoke the central limit theorem right off the bat. And so it starts to limit to something that looks normal. This is incredibly important. So that means you have sample size calibration. You're conditioning on things, and it's changing the dynamics of that distribution. And the Bayesian is not going to invoke normality anywhere in here. They're going to think that distribution looks beta. But it turns out they'll start to agree with somebody that's applying the central limit theorem and thinks that that distribution looks normal. And you'll start to see that that thing looks more and more normal. And if you didn't know that, it would happen for you anyway. And that's kind of cool. What's driving that? The likelihood function, not the prior. So let's just take a moment and see the impact of the prior. So anybody have any other values that you want to entertain for the prior? 500. Which one? You get two choices.
Alpha.
Alpha is going to be 500. You guys are a lively group. What should the other one be? 2. Okay, I've kind of seen something like this. So let's just see. My prior distribution is stacked way to the right. You can't even see it, it's so tight. And I did bound everything on the screen, so I won't make the height of the screen bigger because I just want to focus on what's going on. So your prior distribution is way over here. Saying that, the analysis still did work. If I flipped the coin just a few times, it wouldn't have worked very well. And so I kind of like, I should say it didn't work, the analysis. The likelihood function looks like it's encapsulating the right thing, but my posterior distribution is skewed so far to the right. So basically it's like seeing 500 successes compared to 2 fails, and my 100 data points couldn't overcome that. So this brings about an important property of prior distributions, is they probably shouldn't be ultra concentrated. They should be diffuse for them to be good, and place mass all over the spectrum of P, between 0 and 1. Of course, if Piper knew something about the way I flip coins, and I had some biased coin or something like that, then maybe you could encode it that way. It would be hard to convince somebody of an analysis like this. So you'd need some strong justification. If we didn't want to impose strong knowledge about P, we probably want alpha and beta to be small. And so we can kind of see that in terms of just how alpha and beta appear in the equation and how it compares to the data. So you can think about that as well. Anybody have any other reasonable guesses at what alpha and beta is? I like the spirit because at least it shows us what could potentially happen if we pick really wonky values. So that's a good thing to do. It's something I would do. Let's just really mess with this thing and see what happens. But let's get a little bit more reasonable.
Can you do the uniform?
Maybe a uniform. And so a lot of people do like the uniform prior for this. And the uniform prior corresponds to alpha being 1 and beta being 1. So if I plug in alpha as 1 and beta as 1, those are both zeros up there. And so this is going to be proportional to a constant. And if I normalize it between 0 and 1, the normalizing constant you could probably figure out pretty quickly. So it's 1. So let's just put that in there. A uniform seems like a reasonable guess. Let's just plug those in. Boom. Our prior distribution is now uniform, so it falls into the beta family. Betas are a collection of distributions, and uniform is one such beta. And everything worked out real nicely. So in this case, the likelihood is the posterior distribution. Or at least, I should say that a little bit differently. They look exactly the same. The likelihood needs to be normalized for it to be, and you don't have any right to do that and treat it as a random variable until you go through Bayes' theorem. So Fisher would have liked this analysis. He would have said, yeah, that's pretty good. So I imagine, who knows? It depends on how old Fisher was. I imagine if Fisher was a 35-year-old man, no matter what you'd show Fisher, he wouldn't like anything. And later on, he became more reasonable. So the fiducial analysis is something like taking the likelihood and auto-upgrading it to have a random variable in there. The Bayesian says you can't do that. You need to multiply by 1. So Bayesians have their own hang-ups where it really matters the way you say things to them. And so how you're thinking about everything. I guess it doesn't matter, just as long as you're doing something that's equivalent. So the uniform prior, right here. The uniform prior can have some potential pitfalls as well, that if P were really small, so let's just think about this real quickly. Let's imagine P was 0.0001. And let's say I flip the coin 10 times. Let's say I see all zeros. And that's what you'll encounter in your simulation study. You need to do something about that. And so does anybody know what the maximum likelihood estimate is? So the likelihood function is just P to the sum of the xi's. 1 minus P to the n minus sum of the xi's. So this is a curve and it peaks somewhere. So this is some curve, and this is going to be the max likelihood. The maximum of the likelihood happens here, where it attains its maximum is called the maximum likelihood estimator. So some of you will know, without even if you wanted to figure this out and maximize it, my recommendation is take a logarithm of this thing, linearize that equation, then take a derivative, set it equal to 0, and solve for P. When you solve for P, we'll call that P hat, and in this case, we call that the max likelihood estimate. What is the max likelihood estimate? Yeah, exactly. You can prove that to yourself, and if you don't, we'll do it. It's something. If we are just looking at the maximum likelihood estimator, you might have a problem. So if we were classicists, and we were thinking about the max likelihood estimator, something like that, what you might do is say, I'm going to look at some of the xi's, it's 0. P was ultimately small and n was small, then that would be excruciatingly likely to happen. So if I were trying to estimate the standard error, I might take P hat times 1 minus P hat. P hat in that case would be 0. 1 minus P hat would be 1. And so that would be 0, and I divide that by something. So probably n, and take the square root over the top, it's still 0. And so an asymptotic analysis might fail right there. But a Bayesian is still going to say something totally different. What the Bayesian might like to do is penalize these endpoints. So there's boundary conditions, and it's very typical to take that into account. The uniform prior does not do that. And so there's other priors that we might consider. And you'll be able to explore these. So my favorite prior for this analysis is a beta 1/2, 1/2. And it looks like this. It's this U-shaped thing, and it's penalizing the endpoints, the boundary. So it's placing some mass there. And the idea is that we don't want to say necessarily that the things are 0. So we want to put a lot of mass close to 0 or close to 1 that's going to upweight values around there, so you don't get in this trap of the max likelihood estimate, or the likelihood is not well behaved with small data point. So in some sense, the prior is just acting as a penalty function. I will say something, that if you did construct posterior estimates, intervals based off of that posterior distribution. So if you took the highest concentration of density and I mapped that to an interval, that interval is an optimal frequentist interval. So what I mean by that is if I take the highest density interval that I can form that's 95%, so something that's encapsulating 95% of the mass under that curve, but it's the shortest interval that you can come up with, that interval will be any interval that a non-Bayesian or Bayesian, any other interval in terms of coverage. So if I repeated this study over and over again, and I looked at how often that interval covered the truth, the Bayesian interval would beat everything else. So this is my big gripe when people say there's frequentists and they're Bayesians and they don't get along. This is an example that will demonstrate to you, we won't do it mathematically, but you can do it simulation-wise, that the Bayesian can be an optimal frequentist. Of course, the Bayesian is not necessarily bound by that, but they can do that. That was proved in the 70s. So Jerry Brown over at University of Pennsylvania proved that. And so it's a long-winded proof. So that's kind of nice. It would be nice if there was an overarching theory for when Bayesians were optimal frequentists, and there is not. So there are attempts to do that, construct priors that have optimal frequentist properties. Usually you have to do something very computational. So construct your prior using like some basis function and kind of just iterate through until you construct a prior that has optimal properties. There are theories in one dimension that sometimes map to optimal frequencies. So my favorite prior is the beta half-half just because it has this penalizing term in there. And if you did use a uniform prior, you probably wouldn't be too far off from this analysis. If you had small sample size and P was close to the boundaries, it would make a difference, and I'll let you explore that. Let's just look at one more example. If we did something, so just to keep in mind, if alpha is equal to beta, then this thing is equal to a half. And so you can look up the variance term. If I take alpha and beta large, it doesn't change the mean if they're both equal to each other, but it does change the variance. So again, you want these things to be diffused. So let's just pick these to be really big. 1,000 and 1,000. So at least maybe that's rational, something like that. That it's like I'm not biasing everything, but I am in some sense. That I'm biasing everything towards the middle. You want to ask yourself if that's fair game, and I would say no. There's my prior, very concentrated, and it's taking a long time for my posterior to pull away. You can kind of see it starting to inch towards the likelihood. So that would be a bad analysis. And so if you're not willing to explain where your prior comes from, why you picked it, demonstrate it to people, show it to people, your analysis is probably not worth very much. Some people get overly concerned about the prior distribution, and so you do need principles when you come up with them. A full-blown Bayesian class will teach you some of that. So I will say a couple things. The beta half-half, which is one of the conjugate priors, has optimal frequentist properties. It also turns out it's transformation invariant, meaning that if I work with a transformation of that random variable P, that my properties are going to be preserved as I transform everything. I need to say a lot more about that, but I'm not prepared to do that in this class right now. So again, a full-blown Bayesian class would help you with understanding that. And so there are a lot of properties of conjugate priors that we like. So here's just probably an overgeneralization, but in general, certain particular conjugate priors, so when I pick certain values for the hyperparameters, they induce optimal properties in some sense. So conjugate priors on their own is just something that's convenient for us, but there is a lot of theory to back up our utility in our usage of those. Of course, how you pick the hyperparameterization, we still need to answer that. I'll let you play around with that in the homework set, and I don't tell you whether or not there's a right or wrong answer for what you've done. So I'll give you a lot of flexibility to play around, and basically your job is to explain everything. Let's just see what a Bayesian does real quickly in terms of our problem that we really want to study. So one of our goals is to infer P over 1 minus P. So I could call this something else. I'll call it Z. So this is GP right here. If you transform everything, what a Bayesian will do is they can just directly transform this distribution. They don't have to do delta method or anything like that. And so what I might do is I might solve for P, come up with the inverse transformation. And so the inverse transformation of Z, I'll let you work this out, is just Z over 1 plus Z. Just multiply the 1 minus P over on both sides, pull everything over to one side, and solve for P itself. And so that's our inverse. It's a bijection. So playing around with this thing is relatively straightforward. And so to transform, we just apply our general transformation formula. So pi of Z, I'll write it down like this. Just put the random variable down there. Is going to be proportional to, I'm going to take my P, and everywhere I see P in this analysis right here, I'll plug it in terms of the function of Z. And so that's just going to look like Z over 1 plus Z. This will be raised to the sum of the xi plus alpha minus 1 minus Z over 1 plus Z. You could simplify that if you'd like. And just write it as 1 over 1 plus Z. So this is going to be sum n minus sum of the xi's plus beta minus 1. And then I have this derivative as well. Not a hard derivative to take. I'll let you take it. This distribution has a name. Does anybody know what it's called? I'll be shocked if you know. It's called its Beta Prime distribution. So I can do inference off of this distribution if I want it. Another possibility is to just sample values out of the beta distribution for P and just get these values right here. So I'll just say Pi is distributed according to this function right here. And I could just sample from that beta distribution over and over and over again, and then form Zi is equal to Pi over 1 minus Pi. So I could just empirically compute those, and if I drew this histogram of these things, where I is going to go from 1 to some large number, I'll call it K. K is not N. K is how many times I sample from this beta distribution to understand it. So you could sample a heck of a lot of times for the beta distribution, form that, and these transformed values will follow this distribution, a beta prime distribution. So you don't actually need to know that distribution to work with it. You could compute it simulation-wise. And that's what you'll do maybe in the homework, something like that. And so if I wanted to construct intervals or something like that, I could take those ZIs, take the histogram, and chop off the tails, something like that. So I say a lot of comments about that in your homework. I do give you a lot of room to potentially make mistakes and explore things as well. So I don't tell you exactly what to do. Any questions about all that? This is about what a Bayesian does. So again, lots more conversation about what the prior is and what the properties are. But in spirit, this is how a Bayesian thinks. Okay. I'm going to move on. So we have 2 minutes. I should be able to get through the entire sufficiency principle. So, I'm just kidding, I won't be able to. I do want to say a few things about it. So, I will say that any statistic is some form of data reduction. And we talk about this in chapter 6. So, if I have a collection of data, so consider X is equal to some collection of data. I'll write it out like this. A stack, and I'll call it T of X, this is the notation your book uses, is some form of data reduction. Now, I guess I could say T of X is the identity and this function just gives you back the original vector. And so there's no reduced space that this lives in. So what I'm thinking about is things like sum of the xi's. So in our example right here, the data only depends, the function only depends on the data through sum of the xi's. So you can have that in mind when you're thinking about this. The question is how far can you reduce the data in all kinds of different problems? In some problems you don't have a reduction, and in some problems you do have a reduction in terms of the dimensionality of the space that your data lives in. And so we'll be answering this question next time, is what's the property of these various statistics? And so we'll come back around to this example, but what I want you to be thinking about is, in terms of the binomial Bernoulli example, whether or not I coded the example as binomial or Bernoulli, this function only depends, the likelihood function only depends on the data through sum of the xi's. Later on, we'll come up with a formal definition of what a sufficient statistic is. So please read through that and try to read through the two experimenters. We'll be covering that proof next time. That's it for now, you guys. I'll see you on Friday. I have a question. So I'm just curious what your preference is. Would you guys be interested in a take-home midterm?
Yes. It's going to be harder.
It depends on how you gauge harder. So I will make it slightly more challenging, and it'll probably take you 2 or 3 hours to do versus 50 minutes in class. Think about this next time, and let's just take a vote. And if you guys all agree, you should do a take-home, and you can turn it in the following class, and it'll give you a little bit more time. Unley says no. She might change her mind in the meantime. Again, hard is relative. Thanks, you guys.
Thank you.